Welcome you all for today's lecture on operation and control of DC microgrid. As we all know, currently the whole world is looking forward towards low carbon footprints. Indirectly, maximum renewable presence in any power system will be of high importance. And to achieve those goals, especially a country like India, where maximum solar penetration expected in next 5 to 10 years. And as per the government policy, we are looking forward to as maximum and as high as 100 gigawatt of solar presence in near future within 1 decade. Though it is a huge challenge, but the concept of DC microgrid looks very potential in the presence of renewable energy, where the generation, especially the PV, which is coming from in the form of DC, and the most of the important loads are also of DC in nature. So, to maintain the balance between supply and the load, and when maximum generation are from DC as well as maximum loads are from DC, it is not a bad idea to plan for a mini DC grid to represent DC smart grid or DC microgrid. Especially in case of island mode operations for rural hilly areas, it could be a viable option to go from AC microgrid to DC microgrid. But being said that, DC microgrid implementation become a very big challenge compared to AC microgrid, because there is no frequency presence in the whole grid. Due to the absence of frequency, it is also difficult for us to implement the existing power frequency droop characteristic, which is very popular in case of your AC system, cannot be directly embedded into my DC grid. So, we have to think for more innovations for PV droop characteristics for control mechanism. So, when we have a DC microgrid in place connected to my grid, which is AC in nature. So, now the balance between DC microgrid and AC grid, which is very large in nature, to be maintained by exchanging energy from DC microgrid to AC grid and from AC grid to DC microgrid. During the energy exchange, it is quite challenging, because most of the time the PV and wind generators connected to my DC microgrid do try to operate at MPPT mode, so that the maximum energy can be extracted from the DC grid, catered to its local load, and the excess energy can penetrate to my AC grid. Similarly, when the load of the DC microgrid is more, we can extract power from the AC grid to meet the DC loads. But that case becomes heavily complicated when it is an islanded mode of operation, where the DC microgrid has to balance its energy locally without any grid support. Under those circumstances, we need to have a storage mechanism. As and when there is excess energy available to me, the storage can be charged or the battery can be charged, and when the load is more compared to my generation, the battery can discharge. So, we will have two different kind of operations when the DC microgrid connected to AC grid or when it is operating with its isolated mode. But to achieve all those without the presence of frequency and the control mechanism become very, very challenging. The one important concept here that I like to highlight, now because we have so many cables around in the case of DC microgrid, the voltage setting of voltage level for the DC microgrid become an issue. It is good that you operate with a very low voltage of DC, but when we reduce the voltage, the current is quite high and the cable size keep on increasing. The thickness of the cable is too high. So, preferably we like to operate at 48 volt DC, could be 96, could be order of 300 and 600 volt DC, but for residential area or maybe for any commercial, it would be good to have operation between 48 volt to 96 volts. It is ongoing research in pace, and with a couple of years from now, you will have a clear picture about the standardization of DC grid, so that all the voltage level can be identified, and the devices those will be connected to my DC grid will also follow the standards specified for DC microgrid operation. So, with this introduction, let us get into the operation and control challenges of DC microgrid. Now, one of the major issues today is the controlling of all the generations present within a DC microgrid. Now, there are three major control mechanisms. One is decentralized control, distributed control, and centralized control. And all these controls, depending upon the scenarios, we need to adopt one of those three, so that a better control mechanism can be incorporated for successful operation of DC microgrid. Now, let us begin with decentralized control. In a decentralized control, each source operates independently using terminal quantities. Hence, the reliability inherent in the structure of a microgrid is maintained. However, implementing a control law to operate the system in an optimal fashion is impossible, since each node is unaware of the other nodes in the system. Very merit of decentralized control that it is very robust and reliable, but the problem here, the one generator may not be able to understand the control mechanism or the operation strategy of the other generator. So, there is no communication in place. So, during decentralized control, it is reliable, very proved concept, but there are few challenges because the generators do not speak to each other or talk to each other. Digital communication links, DCLs, do not exist, and power lines are used as the only channel of communications. Now, in case of centralized control, each source is controlled from a single point using a central controller and communication link. So, centralized control is very popular, but a control law can be implemented easily as the central controller is aware of each node in the system. Means the central controller understand what is happening at the PV bus, what is happening at wind generator connected bus, what is happening my battery storage connected bus. So, the centralized control seems to be a smarter one. However, the reliability of the system is degraded as the system depends on the communication link, and due to any reason, if the communication fails, then the centralized control approach may not work well during failure of communication link. Data from distributed units are collected by a centralized aggregator, and the processed and feedback commands are sent back via DCLs. Now, in case of distributed control, though DCLs exist, they are implemented only between the units and coordinated control strategies when they are processed locally. With distributed control, the control function is distributed throughout the network. This strategy improves the reliability of the system over centralized control, as the system can function even a node fails. In case of distributed control, even at a given point, if the generation is disconnected or the node fails, still the control mechanism do follow its functions without fail. Nevertheless, the system is dependent on an external communication link for correct operation. Distributed control is very important, very advantageous, smart, but we need to have an excellent communication link to achieve its goal. Now, there are different type of decentralized control. Let us slowly see, because we talked about decentralized control, centralized control, distributed control, and then we will now try to see what are those schemes available under the heading of decentralized control. One of the very commonly established decentralized control is my droop control, voltage leveling control, DC bus signaling, and power line signaling method. Now, in case of droop control, we all aware in case of a droop, if it could be power versus frequency, or Q versus voltage, or in case of DC it is voltage versus power. Now, when we drop the voltage, certainly the power is going to vary, but depending upon the slope, the magnitude of power variation depends, or vice versa. When power varies, the voltage has to vary, and depending on the slope, the magnitude will be decided. Now, in case of a conventional droop control, the conventional droop control in a DC microgrid reduces the reference DC bus voltage with increase in output current. The equation governing the conventional droop control in a DC microgrid is given by now, if you consider the droop control P versus VDC, as I have mentioned earlier, in the past we used to plot this characteristic where we had P and F for AC networks, but due to the absence of frequency, now we are plotting the droop characteristic for V versus P. Now, for this is the droop characteristic for my DG1, DG2 and DG1, two different DGs, and you could see if there is a voltage drop, certainly there is a power change, or power change leads to a voltage variation. Now, if I do say, now the VDC star is the operational voltage, and that keep on varying with respect to change in my power. One thing is very clear, when the load is more, if the load current is more, if the power extracted from the system is more, then certainly there is a drop in voltage. So, if the load current is high, and I can certainly conclude that the voltage is going to drop. Now, this is basically with respect to my converter, where VDN is the output voltage of each converter, and VDC star which is the reference DC voltage, and IDCN is the output current, and RDCN is the virtual resistance or the droop coefficient. Now, what is the major drawback in droop control? The major drawback is that if the slope is different, then your voltage regulation will keep on varying. If with different slopes you will have different voltage regulation, and that may lead to good voltage regulation or bad voltage regulation. Similarly, when you like to share a load, and that load sharing may be poor depending upon the slope of the droop, and sometime it is excellent depending upon the slope of the droop. So, the conventional droop degrades current sharing accuracy due to the unequal voltage drop across the line resistances. It also results in poor voltage regulation. Now, let us focus in the previous diagram you said V versus P, now it is P versus V. For a given droop characteristic, now you can see this is what the voltage variation it can experience for a power drop between this range. So, if there is a power drop, you could see there is a huge voltage drop, and hence it is of poor voltage regulation. But the same power drop for this characteristic, you could see the voltage drop is of this range, and compared to this voltage drop, you can see the voltage drop is reasonably smaller, and I can say for this red characteristic it has good voltage regulation, whereas for the green characteristic it has a poor voltage regulation for the equal amount of power variation. Similarly, we can see that the given if there is a variation in the droop characteristic, you could see that it's a good load sharing in case of the green one, and whereas a poor load sharing in case of the red one. So, if you indirectly I can say that if you achieve good voltage regulation, you will have actually poor load sharing, and if you have good load sharing, then you will experience poor voltage regulation. So, that is what one of the very common challenge we do face in case of conventional droop control concepts. Now, in case of decentralized droop control, a few further drawbacks that we need to highlight here. Small droop, less voltage deviation between two converters, but less to large difference in current sharing. So, what it wants to say that when there is a small droop gives less voltage deviation. I mean, if there is a small droop, it is a less voltage deviation, but it leads to large difference in current sharing, but it leads to large current sharing. So, if there is a small variation, depending upon the characteristic, you could see there is a huge current variation, and here it is less current variation. So, small droop leads to large current deviation, large droop, small current variation for a given voltage of operation. So, large droop coefficients gives equal loading, but lead to large voltage deviation too. Now, there are few advanced droop control techniques which are in place: virtual resistance based droop control, adaptive droop control, intelligent technique based droop control, mode adaptive droop control. So, virtual resistance based droop control, by including the effect of the line resistance, as I mentioned earlier, that during any control mechanism, in case of a DC microgrid in specific, where the line drops, for example, you have two generators and connected to different cables. Now, if you generate P kilowatt of power, and when it reaches to another node, it is P minus the drop is available to me, and the current flowing in each and every cable is not known to me easily, and hence predicting the generation mix to meet the load, considering the resistance of the cable and the line drops become a challenge. So, by including the effect of line resistances, this control strategy achieves power sharing among the converters. To overcome the effect of line resistance, a virtual resistance RB is considered in the feedback path, and the output voltage equation can be expressed as VDCN equal to VREF plus delta V naught minus RVI, where delta V naught is the compensator output required for restoring the microgrid voltage implemented at secondary control level of, as well as I naught is the output current and RV is the output impedance, and V reference is the output voltage reference at no load. Now, adaptive droop control, an adaptive droop control based on instantaneous virtual resistance RV droop is used to minimize circulating current and current sharing difference between the converters. A figure of merit called droop index, very important, DI, is introduced, which is the function of normalized current sharing difference and output power loss. The expression for droop index for two converter system is given by half of I1 minus I2 plus PL, and that is expected, we have to minimize this function to achieve the DI, where I1 and I2 are the two output currents of the converters, Ni and Np are the normalization of current sharing difference over rated load current and output power loss over maximum allowable upon converter rated power, whereas PL is the converter output power loss. Now, few intelligence technique based droop control over a period of time, like last 1 decade, intelligence techniques become very popular. So, literature justifies that there are few intelligence technique based droop control which are in place. This is a decentralized fuzzy logic based control strategy for multiple distributed energy storage system based DC microgrid. In accordance with SOC, state of charge, of each energy storage unit, virtual resistance are varied using fuzzy logic, because no one knows what exactly the virtual resistance is. So, that will be varied for an optimal operation. So, fuzzy logic based adjustment of virtual resistance reduces voltage deviation in the common DC bus, and it also ensures stored energy balance among multiple distributed energy storage units. Mamdani fuzzy inference system require SOC and voltage error VE as input and virtual resistance as output, means by giving the SOC and voltage error we can calculate the virtual resistance. The equation for voltage error and SOC is given by VE equal to V reference minus VDC, where VE, V reference, VDC are the voltage error, DC bus voltage set point and actual DC bus voltage respectively. Mode adaptive droop control. A mode adaptive droop control is used for a DC microgrid with PV, wind and energy storage system. Interesting. So, now here for varying voltage range, droop control is applied to the utility grid, renewable energy sources and energy storage units. The utility, storage units and the renewable energy sources operate in either the droop control mode or at a constant power mode. Now, we will consider actually 3 different mode of operation, where as we have seen, we will be talking about the utility grid, renewable energy sources and energy storage. So, my utility grid is one of the source for me. I can take energy as it can be source for me, and very rarely it can be sink, but most probably it will be a source for me. And the energy storage is again a storage device within my DC grid, and the renewable energy sources within my DC grid can act as a storage. So, we have 3 sources. The utility grid itself is a energy source, battery a storage mechanism, renewables like PV also my storage. So, there are 3 source of energy, storage, PV and utility grid, and we need to operate all the 3 of them in a different pattern. Now, the mode 1, the first way of operation, this mode corresponds to utility operating in droop control mode. Energy storage and DG are operating in constant power mode. Okay? The utility is in droop control mode, whereas the storage and DG operate in constant power mode, whereas in mode 2, where the energy storage operate in droop control mode, whereas utility and DG act as a constant power mode. Mode 3, where actually we allow the DG to operate in droop control mode, and the energy storage and utility can operate in the constant power mode. If you say it is A, B, C, A, if one of them is at control mode, droop control mode, A is in droop control mode, so B and C operate at constant power mode, and similarly alternatively B is your droop control mode and A and C are in constant power mode, and then C is in the droop control mode, A and B are in the constant power mode. Now, let us move into voltage level signaling approach. Voltage level signaling is a nonlinear form of voltage droop that allows sources to be scheduled in a prioritized fashion. Discrete voltage deviation on the bus provide information about the generation mix to facilitate source scheduling. This strategy departs from the underlying aim of voltage droop to provide power sharing with minimal voltage deviation on the bus. It also takes care of significant voltage deviation are permitted if the system is power electronics based and the source and load interface can be designed to operate satisfactorily within a specified voltage window. The major drawback of voltage level signaling: although voltage level signaling allows source scheduling, this control strategy suffers from two major drawbacks. First, the number of sources in the system is restricted by the operating window of the bus voltage and the line impedance, whereas the second one, adding high priority sources to the system, involves changing the states of all sources with a low priority. Voltage level signaling is suited only for small renewable energy sources where these drawbacks are not a major concern. Now, let us move to DBS method, that is DC bus signaling approach. DBS control scheme is similar to our past voltage level signal, except the system voltage decreases to the next state when the power output from all the sources in the current state and higher state is exhausted. Thus, sources are scheduled in groups rather than as individual sources. DC bus signaling allows more nodes to be included in a system than voltage level signaling, as multiple sources can operate at each state. Sources can easily be added to the system by assigning the new sources to operate at existing threshold. DBS depends only on local information and does not require any other components other than interface converters. Henceforth, it is easy to implement decentralized control method. The key concern here is the selection of appropriate voltage level, that is whether it is 48 or 96 or 300, which are required to identify different operation modes. If the difference between the adjacent voltage level is very big, then the DC bus voltage fluctuation will surpass the acceptable range. Besides, the difference among the voltage level should not be very small, because sensor inaccuracy and the DC voltage ripples could then prevent reliable identification of proper operating mode. So, here what is the issue? The difference need not be very high or neither it is too small. Now, let us concentrate on power line signaling method, so called PLS, which is very interesting. When we talk about power line signaling method for DC microgrid, I do not see anything very special here compared to our old existing power line control approach. I mean, the communication link is being used for our AC grid, but for DC grid it is slightly different, wherein PLS is a decentralized method which can be deployed for coordinated control. The sinusoidal signals of a specific frequency are injected through amplifiers into the DC bus. This allows each device to send and receive information on its status, performance history or internal operational mode. PLS relies on digital communication, but still it is categorized as decentralized because the power network is the only communication medium. In the power system literature, this particular way of communication is something referred as power line communication. As I was mentioning earlier, I mean, the conventional AC system use in the term power line communication, and we here use it as a power line signaling method. So, both approaches are more or less similar. PLS is a very complicated to implement compared to other decentralized method such as DBS and adaptive droop. PLS is commonly used only for changing operation or setting corrupted component of the system, and it is not suitable for power sharing. Different type of distributed control. Distributed control, as we have seen in my beginning of the lecture, where we mentioned the distributed control is very smart and important, and we will see different types of distributed control: digital average current sharing approach, average voltage sharing with pilot bus regulation, distributed cooperative control. And when we move to digital average current sharing, this is a distributed control approach for an accurate voltage regulation and load sharing. It uses communication based digital average current sharing, and the conventional Drup equation is changed by addition of delta Vk as given below. So, you can see the average current expression as well as the Drup equation being changed by addition of delta Vk in this expression. Average voltage sharing with pilot bus regulation. It employs a biproper anti-wind up design for distributed voltage controller to prevent error caused due to compensator saturation. The reference set point is fine tuned to regulate the voltage of pilot bus. The distributed secondary voltage control loops are unified to provide a computed average control signal to the primary controller. Although this approach is distributed, it still depends on low bandwidth communication channels. Distributed cooperative control. A multi-agent based distributed control of heterogeneous storage devices are used, where an ultra capacitor voltage, battery voltage and SOC are controlled by employing a mesh approach. The cooperative control strategy ensures that the storage device does not have energy deficit at any point of time. Centralized secondary control. This voltage control method utilizes a fuzzy logic based centralized controller with a gain scheduling control for DC microgrid and with a electric double layer capacitor as an energy storage. The DC gain is to in according to the output power by gain scheduling control to accomplish better voltage regulation and load sharing. A real time energy management system EMS with an adaptive energy calculator based on the moving average measurement technique is employed in a DC microgrid. The EMS sets the converter to current control mode under grid connected operation, and one of the converter is set to voltage control under the islanded mode. Let us now summarize all the control schemes that we have gone through: centralized, decentralized and distributed, and few important points to be noted as conclusion remarks of basic control schemes. Hierarchical control topology similar to AC microgrid is employed in DC microgrid, but the major difference here is the control approach and choice of control variable such as output voltage of the DC units. So, the AC control approach and DC microgrid control approach are almost similar, excluding choice of control variables, very importantly output voltage of the DC units. Distributed control techniques are also employed, such as model predictive and multi-agent based control approaches. DC microgrid compared to AC or hybrid AC-DC microgrid does not require active power frequency Drup control at primary level in the isolated mode of operation, because during isolated mode of operation it claims that it does not require, DC microgrid does not require active power frequency Drup. DC bus signaling based secondary control of DC microgrid combines the advantage of distributed and decentralized control. These are the following references of today's lecture. Thank you very much.